Hello dear students, today in this session we are going to discuss about photoelectric effect, especially the effects of photoelectric current with various physical quantities like intensity of incident radiation of light, frequency of incident radiation of light, potential difference between the cathode and anode, and also its dependence with the metal used as the cathode. All these things are going to be discussed in this particular heading. We need to know the experimental arrangement first. You might have studied about the photoelectric effect in the previous session, that whenever a light of suitable frequency is made to incident on a photosensitive metal surface, electrons are emitted from the metal surface. This effect is called the photoelectric effect. When light of suitable frequency is made to incident on a given photosensitive material, then electrons are ejected from the metal surface. Simple phenomenon. Incidence of radiation, emission of photoelectrons. Why it is termed photoelectrons? Electrons are emitted because of the incidence of light. Light here refers to photo. So, photoelectric effect. This is the very important experiment which laid the foundation for the beginning of the modern physics, or otherwise you can call it quantum physics. The generation of quantum physics started with these experiments. Wave theory has got its failure in this experiment, and quantum theory got its success. We are going to see how in this lesson. We are going to discuss about what is photoelectric effect, what are the effects of photoelectric current with various physical quantities. We shall discuss one by one. Before getting into that, we shall speak about the experimental arrangement. Let us consider a source of light, yes, which emits electromagnetic waves of known and varying frequency. Known and varying frequency. The intensity of light emitted is I. Intensity of light emitted is I. Let me explain you simply. You may know about the terms what you are going to use here, but it is essential to know about the terms which we are going to discuss here. When you are speaking about the frequency of light, it refers to the energy possessed by the light radiation. For example, we can go with VGR. Red has least frequency, violet has greater frequency. So if I say I am changing frequency, I am changing the colors in a simple way. If I am changing frequency, it means I am going to change the colors. In other words, if I speak about electromagnetic waves, electromagnetic spectrum, we can say there are 7 different radiations: radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and then gamma rays. So radio waves have least frequency, gamma rays have greater frequency. It's the increasing order of frequency from radio waves to gamma rays. So if I say that I am changing the frequency of incident radiation, I mean that if initially I am allowing infrared radiations to fall on the photosensitive metal plate, now I am going to change it to visible light and then ultraviolet light. In this sense, I am increasing the frequency. If I am coming from gamma rays, X-rays, ultraviolet rays and visible light, I am decreasing the frequency of incident radiation. So, when you are speaking about the frequency of incident radiation, then simply you can mean it, you are speaking about the type of radiation. That's the first thing. Then, what about intensity? What is this term, intensity? Intensity of light radiation here refers to the number of photons incident on the photosensitive metal plate. When you are speaking about wave theory, intensity there deals with amplitude. If amplitude is greater, intensity is greater. Amplitude is lesser, intensity is lesser. For example, if I compare two waves, of these two waves, this has a greater intensity. This has a lesser intensity. Why? Amplitudes. When you compare the amplitudes, this one has lesser amplitude, this one has greater amplitude, so we can say intensity is greater. This is in terms of wave theory. When you speak about particle theory or quantum theory, we can say the intensity here refers to number of photons. Lesser the number of photons, lesser is the intensity. Or in other words, I can say intensity refers to brightness. Brighter the radiation, more the incidence of light. Here light is said to consist of photons. So more the number of photons incident on the photosensitive metal plate, more is the intensity. Lesser the number of photons incident on the metal plate, lesser is the intensity. So whenever I am using the term intensity, if I am saying that I am changing intensity, then I am exactly changing the number of photons incident on the photosensitive metal plate. So intensity here refers to the number of photons incident on the metal plate, or in other words, I can say I am changing the brightness of the incident light radiation. Potential difference that you know, these terms are very important. Frequency, intensity. See, I am speaking about the source here. S is the source of electromagnetic waves of known and varying frequency. Known and varying frequency. The source can generate a varying range of frequencies. That is the meaning. For example, I can speak about sunlight. Sunlight is a source of varying frequency. And also, you can speak about intensity. Let I be the intensity of light falling on the photosensitive metal plate. I am not changing the intensity here. For here, I am considering this intensity as a constant. If I need to change the intensity, I can. When I am speaking about blue to yellow, then I am decreasing the frequency. When I am speaking about yellow to blue, then I am increasing the frequency. So that's the key idea. So whenever I am speaking about the change in frequency, I am changing the radiation. That's the meaning. So a source emits radiation of known and varying frequency, intensity is high. This radiation is made to fall on a photosensitive metal plate. This is nothing but a cathode. Cathode C. Cathode C is a photosensitive metal plate. Photosensitive is nothing but light sensitive metal plate. So it is made to fall on a cathode. The cathode emits electrons. Cathode, what is the role of cathode here? Or a negative electrode here. Cathode is otherwise called a negative electrode. So I can write it here. Cathode is negative electrode. Anode is positive electrode. So cathode emits electrons, anode collects electrons, emitted electrons. So cathode is a photosensitive metal plate which emits electrons here. These emitted electrons tend to reach the collector electrode. We call it anode. This cathode and anode are taken in a evacuated glass bulb. They are taken in an evacuated glass bulb. Evacuated glass bulb. What is this evacuated glass bulb? You have reduced the pressure of the gas enclosed inside this discharge tube, which is said to be evacuated, completely removed. Very low pressure is maintained inside the tube. We call it evacuated glass tube. And then the end is closed with a quartz window. And this the path through which the radiation is entering is covered with a quartz window. What is the role of quartz window? It allows ultraviolet and visible light to fall on the cathode. All the other radiations are prevented from not reaching the cathode. So the role of quartz window is to allow ultraviolet radiation and visible light to fall on the photosensitive metal plate. Now, the cathode and anode must be maintained. I told you already, cathode is a negative electrode, so it must be provided a negative potential. Anode is a positive electrode, so it has to be given a positive potential. The potential difference across the cathode and anode is maintained by a high tension battery. It is maintained by a high tension battery. We can show the high tension battery over here. This is a high tension battery, and that is connected to a potential divider PQ. What is PQ here? Potential divider. It's connected to a connected across a potential divider, and a key is connected in series with it. A key is connected in series with it. Now, the cathode is connected to this potential divider exactly at its center tap, or exactly at the central terminal. We call it central terminal. If 10 turns are there, exactly at the 5th turn, the connection has been made with the cathode. That's the meaning, which means that is the neutral point, and that is the point where you will be providing zero potential. So this is the central terminal. This is the central terminal. So I am connecting the cathode C to the central terminal. The anode is connected to a sliding contact. Is connected to a sliding contact J. Anode is connected to a sliding contact J. So you can make this sliding contact to move over this potential divider. As you are moving the sliding contact above this central terminal, then you will be providing positive voltage to the anode. You will be providing positive voltage to the anode. Cathode is already with the negative potential, so that is not a problem here. And if the jockey is taken exactly towards the central terminal, you are providing 0 volt to the anode. This is with respect to cathode. See this one? With respect to cathode. When compared to cathode, anode is at positive potential. When compared to cathode, anode is at 0 potential. When you are taking the sliding contact to the other side, means in the downward direction, in this diagram, then we can say we are providing a negative potential to the anode. So anode can be given a positive or negative potential with respect to the cathode. Even 0 potential can be provided to the anode. So anode can have a positive or negative or 0 potential. But cathode should be provided only a negative potential. Now, we can say here, in order to measure the positive as well as negative potential, a voltmeter is designed to measure this potential in such a way that the 0 is marked at its center. In all the voltmeters, 0 will be at its end, at its one end, and then the deflection will be taking place throughout. But here, in order to measure the positive and negative potentials, we can say a voltmeter which is connected across anode and cathode. See, a voltmeter is connected across anode and cathode, whose 0 is marked exactly at center. Whose 0 is marked exactly at center. It is designed in such a way, and then it is connected across the cathode and anode. And in order to measure the current flowing through the circuit, you are connecting an ammeter in series in the order of microamperes, which is said to have a scale in the order of microamperes. So an ammeter is connected in series to measure the current in the order of microamperes. A voltmeter is connected across the cathode and anode to measure potential difference. And we can say this is the arrangement made. I is the current flowing through the circuit. This is the arrangement made to study the effects of photoelectric current with the various physical quantities. Now you can see here, cathode is connected to a negative terminal of the high tension battery, anode is connected to the positive terminal of the high tension battery as of now. When you move it to the other side, you will be providing negative potential to the anode with respect to the cathode. So in order to have positive or negative potentials, we are using a sliding contact J. Now, in the diagram I had shown you, a source is there. Suppose if no light is made to fall on the cathode, what will happen? What do you observe? There will be no deflection observed in the ammeter, which indicates that there is no current flowing through the circuit. So, I can say, if no radiation is made to incident on cathode, then no current will flow through the ammeter. So there is no deflection in the ammeter. If a radiation of suitable frequency, let us say ultraviolet radiation is made to incident on the cathode. If ultraviolet radiation is made to incident on the cathode, you can see a deflection in the ammeter, as well as deflection in the ammeter, which indicates that there is a current flowing through the circuit. What makes the current to flow through the circuit? It is the emission of electrons from the cathode. As the electrons started emitting from cathode, these electrons travel towards the anode. Anode is the collector electrode, so it collects the electrons, so circuit gets completed, a current tends to flow through the circuit, which is indicated by the deflection in the ammeter. The amount of current flowing through the circuit can be measured using the microammeter, as we saw already. So, when a light of suitable frequency, when a radiation of suitable frequency is made to incident on this photosensitive metal plate, you can say a current tends to flow through the circuit, which can be measured with the help of a microammeter. Here we are going to study about the effects of photoelectric current with the change in the frequency, with the change in intensity, with the change in potential difference across cathode and anode, also with the metal plate used as the cathode and anode. We shall discuss one by one. The heading reads, the effect of intensity of incident light on photoelectric current. What happens if you vary the intensity of incident radiation on the cathode? What is intensity of incident radiation? As we saw already, intensity here refers to the number of photons incident on the metal plate. Before getting into this fundamental, I would like to explain, when one photon is made to incident on the photosensitive metal plate, there will be emission of one electron. If n number of photons are made to incident on the photosensitive metal surface, then n number of electrons will be emitted from the metal surface. The radiation which is made to incident on the photosensitive metal may interact with electron on the metal surface or may interact deep inside the metal surface. If it interacts with an electron on the metal surface, then after ejecting the electron from the metal surface, for ejecting the electron, some amount of energy will be spent. Remaining amount of energy will be imparted as the kinetic energy for this emitted photoelectron. Suppose an electron is taken from the interior of the metal surface, then some amount of energy is spent in liberating the electron from the surface, means from the atom, and then the remaining energy will be imparted as its kinetic energy, but some amount of energy will be spent by the electron to come from the interior to the surface. So some energy will be lost. With the remaining energy, it will be traveling towards the anode. So we can say that radiations of suitable frequency, why do we call suitable frequency? Certain amount of frequency is required. Simply we can compare this with business. Suppose you are going to purchase a product whose minimum value is 100 rupees. Then you must give the shopkeeper a minimum of 100 rupees to buy the product. A maximum can be given by you. You can give 110, 120, 130, whatever. But a minimum of 100 rupees is the essential amount to buy the product. In the same way, an electron which is there on the metal surface has to be removed from the metal surface, then a minimum amount of energy is required to liberate the electron from the metal surface. And the minimum energy or minimum frequency is provided by the source of radiation. For infrared radiation, electrons will not be emitted from the metal surface. For visible light, for some radiations, in visible light, you have violet, indigo, blue, green, yellow, orange and red. For red, there will be no emission of photoelectron, but for violet, there will be an emission of photoelectron. For ultraviolet radiation, there will be an emission of photoelectrons. So, violet, ultraviolet, this kind of radiations possess required amount of energy so that electron can be liberated from the metal surface. That's the key idea. So, we can say the remaining energy is given out as kinetic energy. That also we discussed, right? So, electrons will be liberated out of the metal surface, and the liberated electron tend to travel towards the anode, resulting in a flow of current. We shall see the effect of photoelectric current with intensity. So I can write the heading simply like this: photoelectric current, variation of photoelectric current with intensity. As I told you already, intensity refers to the number of photons incident on the metal surface. Intensity refers to the number of photons incident on the metal surface. In order to study about this effect of photoelectric current with intensity of incident radiation, you have to keep the frequency of incident radiation a constant. For example, I can say if ultraviolet radiation of certain frequency, ultraviolet radiation also has a range of frequency, I am considering certain value of frequency of ultraviolet radiation. That radiation is made to incident on the metal surface, cathode. That is kept constant. You should not vary the value of the frequency of the incident ultraviolet radiation. Frequency is kept constant. Then potential, accelerating potential is also kept constant. Accelerating potential is also kept constant. What else is left there? Intensity is there. Intensity is changing. Correspondingly, what is the effect of current? This is intensity. What is the effect of current? I refers to current. This can be studied here. Before doing so, here the anode is maintained a positive potential with respect to cathode. Anode is maintained a positive potential with respect to cathode. So while studying this effect of photoelectric current with intensity, what are the quantities that are kept constant? Frequency of incident radiation is kept constant. The potential difference applied between the cathode and anode, some amount of potential difference, accelerating potential, is maintained, a constant. Intensity of incident radiation is changing, which means you are going to change the number of photons incident on the metal surface. Initially 10, for example I am saying 10, then 20, then 30. In this way you are keep on increasing the number of photoelectrons or number of photons incident on the metal surface. Correspondingly, electrons will be emitted out. That will be measured as the photoelectric current. You have to maintain the anode with a positive potential with respect to cathode. Anode is maintained a positive potential with respect to cathode. Why? Anode should collect all the emitted electrons from the cathode. Anode should be capable of collecting all the emitted electrons from the cathode. So that must be provided. Anode must be provided a positive potential. Now, the amount of varying intensity is taken along x-axis, and the corresponding photoelectric current measured is taken along y-axis, and a graph is drawn. I can say intensity of incident radiation is taken along x-axis. Photoelectric current is taken along y-axis. A graph is drawn. With increase in intensity, the photoelectric current also increases. Graph is a straight line. Graph is a straight line. So I would like to conclude that the photoelectric current, or when the intensity of incident radiation, that is the number of photons incident on the metal surface changes, then the photoelectric current correspondingly changes, which means photoelectric current is directly proportional to the intensity of the incident radiation. If the number of photons incident on the metal surface varies, increases, then the correspondingly photoelectric current also increases, which means number of electrons emitted also increases. As I told you, for one single photon there will be emission of one electron. If 10 photons are made to incident, there will be emission of 10 electrons. 20 photons, 20 electrons. 30 photons, 30 electrons. So what happens here is the photoelectric current varies directly with the intensity of incident radiation. This is the first result obtained from the experimental arrangement of the study of photoelectric effect. So, effect of photoelectric current with intensity is very simple. When the intensity of incident radiation is varied, then the corresponding photoelectric current is also varied, which means photoelectric current varies linearly with respect to the intensity of incident radiation. We shall see the second effect, effect of potential difference on photoelectric effect. To study the effect of potential difference on photoelectric current, you must keep the frequency of incident radiation a constant, and then the intensity of incident light a constant. Potential is varied. Potential is varied between the anode with respect, or potential of anode is varied with respect to cathode. And we are going to check out what is the variation that has been observed in the photoelectric current. As I told you, initially a light radiation of suitable frequency is made to incident on the cathode. Let us say some ultraviolet radiation is made to incident on the cathode. Then the intensity is kept constant. Let me say number of 50 photons. This is just for an example. This is not in reality. I am just telling you for example. Some 50 photons are made to incident on the cathode. The potential given to the anode alone is varied. Initially, this can be studied with the help of a graph here. A graph is drawn. This is 0 volt. This is collector potential difference, which means the collector potential. This one is retarding potential, decelerating potential, 0 volt. This is photoelectric current, I. Because there is a simple confusion that will always arise here. Photoelectric current is represented I, intensity of incident radiation is also represented as I. So you should not confuse yourself. Here in the y-axis, we are taking photoelectric current as the potential given to the anode is kept positive now. The positive potential is increased. Correspondingly, the emitted electrons also increases. As the positive potential is increased further and further, photoelectric current also increases further and further. And at one particular value of anode potential, the photoelectric current becomes a steady. Photoelectric current attains a steady value, steady maximum value. We call it saturation current. Because this is saturated. Current is no longer increasing as we increase the anode potential. Anode potential is increased further and further, but photoelectric current remains the same after certain value of anode voltage. Why does this happen? Idea is simple. If the positive potential of the anode is increased further and further, what will happen? If the radiation is met incident on the cathode, electrons will be emitted from the cathode. The emitted electrons will possess, different kinetic energy. Electrons will possess different kinetic energy. Electrons will not have the same kinetic energy. Electrons will be different in number and they will possess different kinetic energies. These electrons are emitted from the cathode and they tend to move towards the anode because anode is provided a positive potential. As the electron tends to move towards the anode, each and every electron has its own kinetic energy. Those electrons which have greater magnitude of kinetic energy will reach the anode when the anode is provided lesser amount of positive potential. As the potential of anode is increased further and further, the electrons with least kinetic energy will also be attracted by the positive potential of the anode, so that electron alone, or that electron also will reach the anode. In this way, all the emitted electrons from the cathode tends to reach the anode with certain amount of positive potential provided to it. So if I say, for example, I am saying, if I am applying 1 volt to anode, then some 2 or 3 electrons, then 10 electrons are emitted from cathode. Let me say a simple example, just for an understanding. 10 electrons are emitted from the cathode. I am providing 1 volt potential to the anode. So 2 electrons are reaching. Increasing the potential to 2 volt, 3 electrons. 4 volt, 5 volt, 6 volt, in this way number of electrons goes on increasing. When 10 volt potential is applied, all the emitted 10 electrons tends to reach the anode. So what has happened? All the emitted electrons are attracted by the anode, collected by the anode. So the maximum number of electrons emitted by the collector or collected by the anode, so maximum current is resulting. Shall we expect more number of electrons that can be emitted by the collector? No, because I am keeping the intensity of incident radiation a constant. Intensity of incident radiation a constant. And I told you 50 number of electrons, means photons, are made to incident on the cathode. I just told you 10 electrons. Now, if the intensity is maintained 50, then the emitted number of electrons will also be 50. Collected electrons will be 50. So for each and every second, 50 photons will be incident on the cathode, 50 electrons will be emitted from the cathode, 50 electrons will be attracted by the anode. Is it clear? 50 photons will be incident on the cathode, means intensity is maintained constant. 50 electrons will be emitted by the cathode, because 1 photon can emit 1 electron. This is for a clear understanding. 50 electrons happen to reach the anode. So all these electrons reach the anode, resulting you in a maximum current. There is no possibility of the increase in number of electrons unless the intensity of the incident radiation is increased. If the intensity is maintained a constant, the number of electrons emitted is also maintained a constant. Thus, all the emitted electrons are attracted by the anode. Current has reached its saturation level. So a saturation current, a steady current, tends to flow through the circuit, whatever the potential provided to the anode. If you are increasing the potential beyond 10 volt, let us say 15 volt is provided to anode, what will happen? Voltage is 15 volt, but emitted electrons are only 10 or something, 50. Then the 50 electrons alone will be reaching the anode per second, which means electrons whose count will not change, so the current whose magnitude also won't change when you increase the value of anode potential. So the positive potential can be further increased, but current will not increase. Current will become steady. So this current is termed saturation current. This is how the variation of current with respect to potential takes place. Now, what you are doing is, you are decreasing the value of anode potential. We just started from 1 volt to 10 volt. Now, we are going from 10 volt to 1 volt, then 0, and then to a negative value. Because that is possible with the help of a sliding contact, J, over the potential divider. So, what we can do is, we just start from 10 volt, then decrease the value of potential. Just look at the graph. As the potential is decreased from positive value towards 0, current will also decrease, and then it will fall. Actually, for 0 volt potential, there is certain amount of current. For 0 volt potential, there is certain amount of current which is flowing through the circuit. That is shown in the graph here. How come it is possible if potential is not applied? If potential is not there, how come you get certain amount of current that is flowing through the circuit? We can say here, if the anode potential is maintained at 0 volt, then also there is a certain amount of current flowing through the circuit. This happens due to the emission of electrons which is taking place from the cathode. As the light radiation is made to incident on the cathode, the incident radiations liberate the electron from the metal surface. Those electrons which are emitted may possess maximum amount of kinetic energy. That maximum kinetic energy of electrons supports the electrons to reach the anode, though there is no positive potential provided to the anode. There is no potential to attract these electrons, but there is no such necessity for these electrons having greater amount of kinetic energy. They can manage themselves to reach the anode, resulting in a flow of current. But that current will not be equivalent to saturation current. That will be less than the saturation current, because the emitted electrons are not possessing same amount of kinetic energy. Each and every electron has its own kinetic energy. Where we are focusing is those electrons which possess the required amount of kinetic energy to reach the anode. The fastest electrons which are emitted from the metal surface, which tends to reach the anode, they result in a flow of current, and that current is due to the fastest electrons which are reaching the anode. What about the other electrons? They won't possess that much amount of energy. They must be supported by the positive potential. As we made the positive potential zero, those electrons will not be attracted towards the anode. So out of let us say some 50 electrons, some 30 electrons or 40 electrons may happen to reach the anode if they possess maximum kinetic energy. Right? So they tend to reach the anode, resulting in a flow of current, though the anode voltage is made zero. Now, anode voltage is made negative now. Anode voltage is made negative. You are decreasing. You are moving the sliding conductor down. As you are making the anode voltage negative, then for each and every negative voltage, there is a retardation which will take place. Before going into that, these electrons which are possessing fastest, greater kinetic energy, they manage themselves to reach the anode against the retarding electric field. This is a very important statement. Actually, anode is given a positive potential, cathode is given a negative potential. If it is the case, if anode voltage is made zero, that is different. Anode voltage is made zero, that is different. Before that, when it is given a positive potential, these electrons are moving towards the anode against the electric field. This is the direction in which electric field will act. Positive potential, negative potential. Electrons will be repelled by negative potential. Electrons will be attracted by positive potential. So they move against the electric field in this particular case. Now, we shall go with the negative potential. When the anode is given a negative potential, the negative potential repels the electrons from not reaching the anode. The electrons possess the same amount of kinetic energy, but when they try to reach the anode, when they come close to anode is given a negative potential. If that negative potential is sufficient enough to repel the electron from not reaching the anode, the electrons will be repelled. So the applied negative potential is doing a work against the fastest electron from not reaching the anode, so that the electrons will get repelled. As the negative potential of the anode is increased further and further, for one particular value of anode voltage, negative anode voltage, the photoelectric current becomes zero. Why it happens? At that particular value of anode voltage, negative voltage, the fastest electron of all the electrons also is brought to rest, is stopped, is prevented from not reaching the anode. The fastest electron is also prevented from not reaching the anode. So, by applying that particular potential, all the electrons emitted from the cathode are prevented from not reaching the anode. The potential at which this particular action happens is called stopping potential or cutoff potential. When you complete the graph, you can show like this. As the negative voltage is increased, the photoelectric current decreases further and further. For one value of negative voltage, that is minus V naught, the photoelectric current becomes zero. The potential at which the photoelectric current becomes zero is called stopping potential or cutoff potential. We call it minimum negative or retarding potential. The minimum negative or retarding potential given to the anode with respect to the cathode, which is just sufficient enough to prevent the electron from not reaching the anode, which is just sufficient enough to prevent the electron from not reaching the anode, is called the stopping potential or cutoff potential. The minimum negative or retarding potential provided to the anode for which which is just sufficient enough to prevent the fastest electron from not reaching the anode is called stopping potential or cutoff potential. Right at that particular potential given to the anode, photoelectric current ceases. There will be no flow of photoelectric current through the circuit. So this happens at the stopping potential. Now we can say if initial kinetic energy possessed by the electron is maximum, let us say maximum, we are doing a work against this maximum kinetic energy by applying negative potential to the anode to bring the electron to rest. So we can say the work done in bringing the fastest electron to rest is equal to the maximum kinetic energy of the fastest electron. What is the amount of work that is spent? That is equal to the maximum kinetic energy possessed by the electron. If K maximum is the maximum kinetic energy, which is equivalent to half of V maximum square, then we can say this is equal to EV naught, where in electrostatics you might have come across this expression W equals Q into V, work done equals charge into potential difference. Work done equals charge into potential difference, or potential difference V equals work done divided by charge. So W equals Q into V. Instead of Q, I have taken E because E is the electronic charge. And instead of V, I am taking V naught. V naught is the stopping potential. So this is the amount of work done in bringing the electron to rest. So work done in bringing the fastest electron to rest is equal to the maximum kinetic energy of the fastest electron. So we can say V maximum can be calculated here. This is equal to 2 EV naught divided by m square root. V maximum equals square root of 2 EV. I can substitute for these values or V naught. 1.6 into 10 power minus 19 is the electronic charge. Mass is 9.1 into 10 power minus 31 into V naught. This is also in root V maximum. If you calculate this, you will have 5.93 into 10 power 5 root V naught. 5.93 into 10 power 5 root V naught. This is the maximum velocity. Depending upon the stopping potential V naught, we can speak about the maximum V maximum velocity, or otherwise we can write V maximum is directly proportional to, or if this value is a constant actually, the charge of the electron and mass of the electron is mentioned here. So V maximum is directly proportional to square root of V naught. This is an important result which we are obtaining from effect of potential difference on photoelectric current. Here we are coming across two important things. One, saturation current. Another one, stopping potential. For positive potential, for positive anode potential, the current increases. As you go beyond a particular value of positive potential, the current becomes saturated. As you are coming to zero, photoelectric current is not becoming zero. This happens because the electrons are emitted from the cathode with finite velocity. Then, if you are taking the potential of the anode to a negative value, the photoelectric current starts decreasing. As the stopping potential, or as the potential comes to a negative value, minimum negative value, or a retarding potential is reached, then the photoelectric current becomes zero. Here, the fastest electron is brought to rest with the help of the negative potential applied to the anode. Negative potential applied is doing a work against the fastest electron from not reaching the anode. So electron is brought to rest. So there is no photoelectric current resulting in this particular case. Now, if the intensity is changed, instead of 50, I am changing it to 100 photons and then to 150 photons. If I am changing the intensity of incident radiation, correspondingly saturation current also increases. Saturation current also increases. If you are clear with the idea of what we discussed, then this is very clear. Saturation current also increases. Why saturation current? This is for intensity I1, this is I2, this is I3. I3 is greater than I2 greater than I1. For 150 photons, there will be emission of 150 electrons. So, current will be maximum. When you are reducing the number to 100, intensity is decreased, 100 electrons will be flowing, so current will be decreasing. For 50 photons, 50 electrons. So greater the number of photons incident on the metal surface, greater is the emission of electrons, maximum is the current, or greater is the current. So we can say as the intensity is increased, correspondingly the photoelectric current also increases, which means the saturation current also increases. But the stopping potential remains same. Stopping potential remains same. Whatever maybe the intensity of incident radiation is. Why stopping potential is same here? Though we have changed the intensity of incident radiation, we haven't changed the frequency of incident radiation. Let's consider here. You should not get confused here. If I say a green colored light, or for example ultraviolet light is considered, if this ultraviolet radiation is met incident on the metal surface, the same is maintained throughout this particular experimental study. So ultraviolet radiation is maintained the same. So energy of the photon incident on the metal surface remains the same. So emitted electron has the same amount of kinetic energy. Emitted electron has the same amount of maximum kinetic energy. So the potential required to stop the electron possessing maximum kinetic energy from not reaching the anode will be the same. Is this clear? As the incident radiation has the same frequency, which means ultraviolet radiation is incident. So the emitted electron will possess the same amount of kinetic energy. With the same energy, it tries to reach the anode. We are providing negative potential, stopping potential, and this stopping potential is sufficient enough to stop the electron which is possessing maximum kinetic energy. There is no need to change the retarding potential or stopping potential, right? So intensity variation increases the number of electrons emitted. It won't change the kinetic energy of the emitted electrons. As long as the kinetic energy is maintained a constant, the stopping potential will also be maintained a constant. Intensity variation varies only the number of electrons. So it varies the current, not the stopping potential. So from this we can conclude the stopping potential, maximum kinetic energy of the photoelectrons is independent of intensity. How? As stopping potential is constant, maximum kinetic energy is constant, then we can say as stopping potential has no dependence with intensity, maximum kinetic energy also has no dependence with intensity. So simply we can say maximum kinetic energy of photoelectrons is independent of intensity. Maximum kinetic energy of photoelectrons is independent of intensity. And the same maximum kinetic energy is directly proportional to the frequency of incident radiation. So maximum kinetic energy is directly proportional to frequency of incident radiation. So maximum kinetic energy is independent of intensity. If maximum kinetic energy is directly proportional to frequency of incident radiation, then we can say stopping potential V0 is directly proportional to the frequency of incident radiation. Stopping potential V0 is also directly proportional to the frequency of incident radiation. We shall discuss this dependence as the next effect. We shall see the next effect of frequency of incident radiation on stopping potential. In order to study about this effect, we are going to keep the intensity of incident radiation a constant, which means the number of photons incident on the photosensitive metal surface is maintained a constant. We shall draw a graph to understand this effect. Same kind of graph. This is collector electrode potential. collect electrode potential. On the other hand, or on the other side, there is a retarding potential. There is the photoelectric current. As it is mentioned, intensity of light is maintained, intensity of incident radiation is maintained a constant. As we saw in the previous effect, as the positive potential given to the anode increases, photoelectric current also increases, and then it becomes a constant for one particular value of anode voltage, and then it gets saturated. As you are decreasing the value of anode voltage from positive value to 0, then also there is a certain amount of photoelectric current, which is due to the maximum kinetic energy possessed by the electrons. So we are providing negative potential to the anode, so the number of electrons reaching the anode decreases gradually. As the anode voltage is made to attain a particular value, that is a negative value minus of V0, then the photoelectric current ceases. There is no photoelectric current resulting in the circuit. And this is for a particular frequency, let us say nu1. For example, I can say, just to have a clear understanding, I am considering visible light, of which we are making green light to incident first. Green light has lesser frequency. So green light whose frequency is taken nu1. Green light is made to incident on the photosensitive metal surface. For that, this is the kind of graph obtained. Intensity is same. 50 green photons are made to incident on the photosensitive metal surface. Idea is clear. Now, the same 50 number of photons, but with blue color. But with blue radiation or blue photon is made to incident. Means I am changing the frequency. I am changing it to nu2. What will be the kind of graph obtained? The graph remains same, but as the frequency is increasing, the stopping potential is also changing. I can mark this as minus of V01. This can be taken as minus of V02. So the stopping potential also increases. Why? As the energy is increased, the amount of energy that must be spent to liberate the electron from the metal surface is the same. The remaining amount of energy is imparted as its kinetic energy. As energy is increased, kinetic energy of the electron increases. In order to stop that electron, you must provide a greater amount of negative potential. So stopping potential also increases. For example, you are given 100 rupees. The cost of a particular eatable is 40 rupees. So you are spending 40 rupees there. What is the remaining amount you will have? 60. That 60 is considered as kinetic energy now. What is that 100 called? Frequency. 100 is frequency. Now, you have 150 rupees. The product whose value is the same, 40 rupees. What will be the remaining amount here? You will have 110 rupees. So what has happened here? What is the term given for that remaining amount? I call it kinetic energy. Initially, for 100 rupees, remaining amount was 60. For 150 rupees, the remaining amount is, let us say 60 plus 50, 110. So, what happened? Kinetic energy is increased. What is this initial amount? Initial amount is considered frequency. So, 100 is made 150. Frequency is increased. 60 becomes 110. Kinetic energy also increases. So, this is not corresponding. Actually, the kinetic energy variation is not proportional with the frequency. But thing is that as the frequency increases, the stopping potential also increases. So this is for nu2. And for another frequency, let us say nu3. Let us make it as 200. Let's make it as 200. This is minus of V03. Minus for 200, the remaining amount will be 160 rupees. So kinetic energy increases further. So we can conclude as the frequency of incident radiation increases, then the stopping potential also increases. Stopping potential also increases. As the frequency of incident radiation is increased, the corresponding stopping potential also increases. So we can say this happens because of this particular reason. Why? The kinetic energy of the emitted photoelectrons increases with increase in frequency. So in order to stop that, you must do more amount of work. As the kinetic energy is more, you must do more amount of work to prevent the electron from not reaching the anode. So stopping potential also increases. This is the kind of graph. Intensity is maintained a constant. This is the saturation current. This is the saturation current. Intensity is maintained a constant. Intensity is not varied. This is the saturation current. So saturation current remains the same as it is. But with the increase in frequency, there is a change in the stopping potential. There is an increase in the stopping potential. So we can say stopping potential varies with frequency. Stopping potential varies with frequency. Now, we shall go for another graph from the same idea by taking two different metals. We are going to draw a graph by taking frequency of incident radiation along x-axis and stopping potential along y-axis, and we shall check out what is the variation that is taking place between this stopping potential and frequency of incident radiation. So, in the previous heading, the effect of frequency of incident radiation on stopping potential, we saw as the frequency increases, the kinetic energy of the emitted photoelectron also increases. So the work done in bringing the fastest electron to rest also increases, which means the stopping potential also increases. So as the frequency increases, the stopping potential varies correspondingly. This is what we saw in the previous heading. Now we shall speak about a graph with frequency of incident radiation along x-axis and stopping potential V0 along y-axis. This is taken for two different metals. Let us say metal A and metal B. Metal A and metal B. What happens? When the frequency of incident radiation is increased, the stopping potential also increases. This is what we saw. When the frequency of the incident radiation is decreased, the stopping potential also decreases. For one particular value of frequency, let us say nu naught for suffix A. For one particular value of nu naught, we call it threshold frequency, which is a minimum frequency. The threshold frequency. When the frequency reaches the threshold frequency, there is no longer the emission of photoelectrons. Then there will be no requirement of stopping potential here. Stopping potential becomes zero. What does this mean for this particular metal, for this photosensitive metal A? A particular frequency is met incident on the metal surface, electrons are emitted from the metal surface, the anode is given a positive potential, then gradually decrease to zero, and then a negative potential. When negative potential is given to the anode, the electrons are prevented from not reaching the anode. Right? If frequency is decreased, the amount of stopping potential that must be provided to the anode is also decreasing. Because in the previous heading we saw stopping potential varies correspondingly with the frequency. If frequency decreases, stopping potential decreases. If frequency increases, stopping potential also increases. So, as the frequency is decreased gradually, stopping potential also is decreasing. See this one? Frequency, stopping potential. Frequency decreased, stopping potential decreases. Frequency decreased further, stopping potential decreased further. For particular value of frequency called threshold frequency, the stopping potential becomes zero. What happens at this particular value of frequency? As I started with the green, then blue, like that I just went on. Instead of green, what happens when yellow light is made to incident on the metal surface? Simply, I would like to give out the same example. Product whose value is 40. You have had 100 rupees, so you got a remaining of 60. Suppose you are having 50 rupees. What will be the remaining amount? 40 is spent, 10 will be the remaining amount. You are having 40 exactly. You can buy the product. You are having 35 rupees. Product will not be given. Right? You cannot buy the product because you are having lesser amount than the required. Required amount is 40, but you have only 35 rupees. In the same way, If the electron must be liberated from the metal surface, then that must be provided this much amount of minimum energy. We call it minimum frequency, otherwise threshold frequency. If this frequency is provided, there will be emission of photoelectrons. If the frequency is increased, there will be the emission of photoelectrons with greater amount of kinetic energies. Correspondingly, a stopping potential is required. At the threshold frequency, electrons will be liberated from the metal surface, but it will not move towards the anode because they won't possess the required amount of kinetic energy. If the electrons possess no kinetic energy, then there is no requirement to do a work against the electron because electron itself is there near the cathode. It is not reaching the anode. So work done is zero, stopping potential is zero. If the frequency is greater than this nu naught A, if it is greater than the threshold frequency, then there will be the emission of photoelectrons with kinetic energies. In order to stop those electrons, we need to apply a stopping potential. This happens for both the metals. Let us say metal A, metal B, nu naught B. And what is the difference between nu naught A and nu naught B? Stopping potential means threshold frequency for one particular metal will be one value. For some other metal will be some other value, which means threshold frequency is different for different metals. It is not the same for all the metals. The rate for different products, different goods will be different. You cannot buy all the products with the same value, same amount. Right? A refrigerator, a washing machine, a television are all sold at a flat rate. It is not at all possible. Each and every product has its own value. In the same way, each and every metal plate has its own threshold frequency. You can take out an electron from a particular metal surface very easily. From some other metals, you cannot take the electron without any effort. You have to spend more amount of energy. That's the difference. So, greater the threshold frequency, greater is the amount of energy required to liberate the electron from the metal surface. That's the meaning. So, the threshold frequency is different for different metals. This is the conclusion obtained from this graph. Also, in order to obtain photoelectric effect, in order to get photoelectric current, the frequency of the incident radiation on the cathode must be greater than the threshold frequency. Must be greater than the threshold frequency. If the frequency goes to threshold or less than threshold, equal to threshold, emission is possible, kinetic energy is zero. Less than threshold, there will be no emission of electrons themselves. Right? This is the conclusion obtained from this graph. So, in order to have photoelectric effect, the basic requirement is there should be a minimum amount of frequency of incident radiation that should be made to fall on the cathode. The minimum frequency of the incident radiation below which there is no emission of photoelectron is called threshold frequency. So that is the ceiling, that is the critical value. Threshold is nothing but a critical value, above which there is a emission of electron, below which there is no emission of electrons. We call it threshold. So from the graph, we can say the stopping potential varies linearly with frequency. As the frequency increases, stopping potential also increases. Frequency decreases, stopping potential also decreases. Frequency reaches the threshold, stopping potential becomes zero. Stopping potential becomes zero. From all these results, we are going to list out the laws of photoelectric effect. From the results obtained, we shall speak about the laws of photoelectric effect. First one, for a given frequency, the photoelectric current is directly proportional to intensity of incident light. Photoelectric current is directly proportional to intensity of incident light. I here refers to photoelectric current. So photoelectric current I is directly proportional to intensity of incident light, and this happens only when the frequency is above the threshold frequency. For a given frequency, which means frequency is greater than the threshold frequency, photoelectric current is directly proportional to intensity of incident light. Here we have to speak about an important idea that if the frequency is maintained below the threshold frequency, but the intensity of the incident radiation is increased further and further, what will happen to photoelectric current? It will be zero. Photoelectric current will be zero. Number of photons incident is made 10, 20, 30, 40, but there will be no emission of photoelectrons. Why? Because frequency is less than threshold. So, in order to have photoelectric current, photoelectric emission, the basic requirement is the frequency of the incident radiation must be greater than the threshold frequency. Frequency must be greater than the threshold frequency. Then we can say photoelectric current I is directly proportional to intensity of incident light. Also, we can say saturation current is also directly proportional to intensity of incident light. Saturation current is also directly proportional to intensity of incident light. This is the first law. Second law is that the maximum kinetic energy of the photoelectrons is independent of intensity of incident light. Maximum kinetic energy of photoelectron is independent of intensity of incident light. Also, we can say the maximum kinetic energy of photoelectrons is directly proportional to frequency of incident light. So, maximum kinetic energy is independent of intensity of incident light. Whatever the intensity of incident light may be, maximum kinetic energy has no dependence because stopping potential is same for different intensities. If stopping potential is same, kinetic energy has a dependence with stopping potential. E maximum equals EV naught. So maximum kinetic energy is also independent of intensity. Maximum kinetic energy is directly proportional to frequency of incident light. Greater the frequency, greater is the kinetic energy of the emitted electron. Lesser the frequency, lesser is the kinetic energy of the emitted electron. So we can say frequency has a dependence, or stopping potential has a dependence with frequency. So kinetic energy and the stopping potential are also dependent on each other. But maximum kinetic energy, frequency, stopping potential are independent of intensity. Right? Maximum kinetic energy and stopping potential are independent of intensity. They are dependent upon the frequency of the incident light. Then, fourth one. For a given photosensitive metal surface, there is certain minimum frequency, called threshold frequency, below which the emission of photoelectrons is not possible completely. So there will be no photoelectric current. So for a given photosensitive metal, there will be a photoelectric current only when the frequency is greater than the threshold frequency. So we can say here, for a given photosensitive metal, there is certain minimum frequency called the threshold frequency, below which the emission of photoelectrons is not possible. Thus, there will be no photoelectric current in the circuit. This is about the frequency of incident radiation. And finally, we can say there is no time lag between incidence of radiation and emission of photoelectrons, which means if the radiation is met incident on a metal surface, electrons will be emitted right that instant itself. There is no time lag. So there is no time difference between the incidence of radiation and emission of photoelectrons. When radiation or met incident on a metal surface, electron will be liberated out of the metal surface. Thus, we can conclude for a given frequency nu greater than nu naught, photoelectric current I is directly proportional to intensity of the incident radiation. Also, saturation current is also directly proportional to intensity of incident radiation. Second one, maximum kinetic energy of the emitted photoelectrons is independent of intensity of incident radiation. The same maximum kinetic energy is directly proportional to the frequency of the incident radiation. And then for a given photosensitive metal surface, there is certain minimum frequency called threshold frequency. That threshold frequency corresponds to that particular metal surface. So this metal responds to this particular frequency. Below that frequency, this metal will not respond. This metal will not liberate electron. That's the meaning. So for a given photosensitive metal, there is a certain minimum frequency called threshold frequency. Below which the emission of photoelectrons is not possible completely. However high the intensity of incident radiation may be. See the statement. However high the intensity of incident radiation may be. You can increase the intensity to any number, but there will not be emission of any single electron from the metal surface because frequency is less than threshold. So in order to have photoelectric effect from a given photosensitive metal surface, the frequency must be greater than the threshold frequency. And finally, there is no time lag between the incidence of radiation and emission of photoelectrons. Time lag. In the sense, if photons are incident on the metal surface, electrons will be liberated out of the metal surface. This happens simultaneously. There is no time difference between these two actions. After having a clear idea about experimental study of photoelectric effect, people started giving theoretical explanation for these experimental studies. They started giving out explanation on the basis of wave theory, but it became a failure. We are going to discuss in the next session about what are the failures of wave theory in explaining photoelectric effect and what causes the origin of quantum theory. That we will be discussing in the next session. Thank you.